Hi folks, I want to talk to you today about how to prepare your 3D model files for 3D printing. 3D printing is a great way to accelerate and up your prototyping game. You can do things with 3D printing and printing in basic plastic materials that are just leagues ahead of usually what you can do with cardboard or plywood in terms of like making enclosures or cases or boxes or other components for your physical computing projects. If you're good at 3D modeling for solid geometry, you can design whatever you want in a product like 3D Studio Max or Rhino or Fusion 360, any of those software programs will let you do solid modeling. You do want to be a little bit careful if you're used to Maya or something like that. For instance, the surface, like infinitely thin surfaces or textures that are bump maps. Those things don't print because they're not solid geometry. So you do want to make sure that you're working with solid geometry for 3D printing. If you don't have a lot of experience with 3D modeling, I've added a tutorial for Tinkercad, which is a free browser-based modeling program by Autodesk that's great for getting started in solid modeling. It's very easy to use. And there's also this website, Thingiverse, where people openly share 3D model designs that they've made. So if you're looking for something basic like an Arduino case, you might be able to find it on here and just download the STL files for free and go from there. So to demonstrate how we prepare for 3D printing, that's what I'm going to do. I'm going to look for a Circuit Playground Express case. Okay, here we go. Here's a Circuit Playground one-piece snap fit case that I'm going to use to demonstrate how we do the print, and you may have seen this case in some of my other videos that I use to protect my Circuit Playground a little bit. So we go into Thingiverse, we say download all files, we wait for it to show us an ad, and we download that file, and I'm going to unzip it, and here we go. So we've got a F3D file and the STL. The STL is what we want to work with in Cura, which is what we're going to use to slice this model. So the 3D printers I'm going to show you about today are FDM printers, or fused deposition modeling printers. They work by extruding a thin line of plastic filament and in layers, one on top of the other. So basically, if we were to take this and slice it into like 100 thin little slices, that's how the printer is going to print them, one slice on top of the other. But from our model, we need to tell the printer how to do that, and we use something called G-code to do that, but we don't write the G-code ourselves. We use a slicing software program to take the model, chop it up, and turn it into G-code for the printer. And to do that, we need this STL file. So STL is for stereolithography. It's a very old 3D model file format that actually originally came out of like the medical industry. And it's pretty ubiquitous. It's like the PDF of 3D model files. It's very easy to turn something into an STL, but then trying to turn an STL into anything else is a bit of a challenge. So whatever program you're using to generate your 3D models, you should be able to export to STL as well. Okay, so we've got that. Let's look at Cura then. So this is Ultimaker Cura. It's a free slicing program made by the company that makes the printers in the makerspace. So that's really nice. what's really cool about it is that they haven't like locked it down and made it super proprietary, so that you can actually use Cura with a whole range of other 3D printers made by other companies as well. So if you learn this one, you're in a pretty good place to work with other 3D printers that use the fused deposition modeling method. So the first thing I'm going to do is up here, I'm going to select the printer. So I'm going to use the Ultimaker S5 in the lab. We also have some S3s. They're just a little smaller in terms of the build volume. Either of those is fine. And I'm going to open my file from my downloads. Here we go. And the STL. And if I exported that right at the right size and using millimeters as units, it should come in automatically at the right size. And that looks about right to me. Sometimes you'll see something come in very small or very big, and that usually means it was designed in inches, and you just need to scale it, usually by some multiple of like 2540, because there's 25.4 millimeters in an inch to make it the right size for this, which works in millimeters. So what else do we have here? We've got our like commands over here. We've got some tools over here, and we'll look at some of these things to see our model. If I right click and drag, I can sort of orbit around here just to see what I'm looking at. If I select my model, you'll see I get some controls in these tools up here, and we'll just look at a few of these. I can use these handles to move this object, or just click it and free drag it around the space, and then it will show me like how I've moved it in relation to the origin. I can scale here, so if I wanted to do that percentage scaling for like inches to millimeters, I can do that here, or I could, do some slight modifications to my object. If for some reason I wanted to print this really big, I could do that, or really tall. I could uncheck uniform and make it really tall. I can rotate my object. This is something that will happen too. This one came in nicely where the surface side that I want down is down. Sometimes you'll get things that come in at 90 degrees, and this would be problematic to print, and I'll tell you why. The printer works at the base level here and then moves up. So you really generally want like the flattest surface, the flattest, largest surface to be down on the bed. And so looking at this, that's this side here. This edge is round, obviously that's not great. The top edge is all these little geometry, that's not great. And then in terms of support, the material comes out of the nozzle, and it has to print onto something, so there has to be something below it when it's going up, or the material just falls into space, right? So if I continued rotating this, there'd be some problem areas looking at this. These little arches on the sides, those are actually okay, because it can do some arches. Even those little flats there are probably going to be fine because it can bridge a small gap. The thing that would be really problematic though is these inside surfaces. You can see they're red, and that means that they're unsupported. So that material, when it goes to print that layer, it would just print into nothingness and it would fall, and so it would not actually come out looking the way this looks. It would be deformed. So we want to make sure that the flattest side is down, but also that all the geometry looks like it would be easy to print from that. And I'll show you some other ways we can preview this in a moment. That's rotating. What else? I can mirror, multiply the part, etc. But I think that's good for what I'd like to do. So let's look at some of the other things that the software does. Here is where I select my material, and the S5 has two nozzles. So in that situation where I had this upside down and I said it needs some support, I could use two materials and print in like my main plastic and a supporting plastic that I would break away afterwards. is an option. I can even print supporting material with like the same material, but again, I'll look at that in a minute. For most of what we're gonna do though, the simple kind of like cases and things we'll be doing, one material is fine. Another option to do with two materials, if you want to print something in two colors, like, and you don't want to paint it, you want it to actually be like black plastic and red plastic, we can do that with the two nozzles pretty easily, so that's cool. But I'm just going to show you one for now. So if I click on here, it'll show me the two print heads, and I'm saying my second one is not enabled. I'm not going to use it. The first one I am going to use, and I'm going to select the material and the print core. So that's the nozzle on the machine. Almost all the time it's going to be this AA.04 for what we're doing in the labs, because that's the one that we've got for use with our PLA plastic. In here we can select a bunch of different kinds of materials. So polylactic acid is a very common good material for these 3D prints. It's made from cornstarch, and it prints very easily, very nicely. It's not very finicky. I like it. It's not food safe. You wouldn't want to print anything you're going to eat with this, but it's just a good material. It's also not heat resistant. So if you print something in PLA, leave it in your car on a hot summer day, come back in a couple hours, it won't be a puddle, but it will be wiggly after that experience. So if you need something that's a bit stronger, that can withstand that like summertime car temperatures, that's when you'd want to use a PETG material, PTG, which is like what milk cartons are made out of. That's a good material for strength, for heat. It's a little bit harder to work with though. You really have to dial in the settings for it. Similarly, another resistant one is ABS. ABS is a very common plastic in manufacturing. You might be familiar with it because Legos are made out of ABS plastic. Very durable, very strong, but also very temperamental for 3D printing. It needs to have a sealed environment, a heated environment, even like a little, someone like waving their hand in front of the print can crack it or warp it. A little draft like that can upset the printing process. So you have to be very careful when you're printing ABS. So again, I really recommend PLA for when you're starting out with 3D printing. And now you'll see here we can do a generic material or an Ultimaker material. And if we look at Ultimaker materials, they will have like black PLA, red PLA, etc., different kinds of nylons or ABSs. They've got tough PLA, which is kind of stronger. TPU is cool. It's like a slightly flexible material. It's got 95A shore hardness, so it's like a hard rubber. These specifically refer to PLAs or materials that are Ultimaker branded. The beautiful thing about it is that the spool of material has a chip in it, and when you load the spool into the machine knows exactly what that material is, how much of it is left on the spool, the exact settings that are perfect for that material and the printer that you've put it on, and it does like all the work for you, and you almost know that you're going to get a good print from that combination. So that's beautiful. Of course there's a downside, and it's the economics. It's quite expensive for these spools. These spools are about, I want to say they go for around $50 for a like 750 gram spool of material. That's expensive for PLA. If I go back to generic and just like generically PLA, you'll see like I can't select the color or any other property of it. That spool, if I get something like Overture or Hatchbox, it's going to run me about $20 for a kilogram or 1,000 grams of material. So I get more material for less money. But I'll have to do more setting dialing in here. I'm going to show you some of that, but I'm not going to go into like extreme detail on it. Just to say that you may have to do some experimentation, and I would not expect my first print to be perfect using the generic material. It might come out fine, but it might not. So what you want to use is up to you. The important thing is that you get 2.85 millimeter filament, not 3 millimeter filament, not 1.75 millimeter filament. It has to be 2.85 millimeter filament. I've personally been using Overture filament on the machine that we have in the lab, and it's been working great. And again, I'm not like endorsing one brand or company over another. I'm just telling you my experience. I have no financial connection with any of them. Yeah, so you are responsible for getting your own material for your prints. I recommend getting it online. And again, it's up to you if you want to go generic or Ultimaker. I'm going to show you the process for the generic. It's very similar to the Ultimaker process, except the Ultimaker process is even easier. So we've selected our material. In either case, if I'm using the Ultimaker PLA or generic PLA, I'm going to use the AA.4 nozzle, and that's that. And I'm going to click to get out of there. Then I'm going to go over here, and I'm going to go to my recommended settings. If you don't see this, you can click that, recommended or custom to depends on how deep you want to go with the settings. And so at the top here, we have some profiles, infill, support, and adhesion. And we'll look at what those are. The profiles here are, you're selecting a combination of like speed, aesthetics, and precision, okay? So the printer can print something very precise or very nearly identical to your model by using thinner layers. But the thinner the layers, the longer it takes to print. I can use a thicker layer height, so it'll print less layers overall, but it will take more time. And so we can see these default ones here, 0.6, 0.1, 0.15, and 0.2. They're really like duplicitous of these other settings. So if I want to print fast, I want a 0.2 layer height, and that's like a draft, right? So if I want to see if my print even works, if it's going to be close to what I want, I know I'm going to print more than one, I might print a draft first. Or if I don't care about the extreme precision or visual aesthetics of it, I can go fast and print it at 0.2. If I care more about the visuals, I don't want to see those layers as much, or if I'm doing something really precise, I want like mechanical things to fit together, then I might do an engineering print at 0.1 or a visual print at 0.1. And then if I want to go crazy, I could go down to 0.6. I'm going to leave this on engineering 0.1 because this is a snap fit part. I want it to snap fit, so I want it to be pretty precise when I print it. In terms of infill, this is how much material I want to, or how solid I want the part to be. So how much material is going to print inside the walls of this part. So the printing companies figured out pretty early on that you don't actually need a solid part all the time. You can make a part that's mostly hollow, that has some minimal structure on the inside, and it will still be functional. It makes the print go faster, and it saves you material, so the part's less expensive. And so this is just a percentage of how much infill you want. 100% will be a solid part. 0% will be a hollow part. That can sometimes be problematic because we get into that overhang situation again, where like internally there might not be support for the material. So generally, I'd say for most stuff, 20% is great. If I'm doing something that's really going to be under stress, like a gear, I might go up to 50%. But generally, 20% is fine. Support, I'll look at in a second. Support, checking that will help me try to print those overhangs. This part doesn't have any the way I've oriented it, so it should be fine. And then adhesion will help it stick to the bed when we're printing it. Sometimes that first layer it prints doesn't stick that great to the bed, and if it doesn't, it can break off like halfway through your print, which ruins the part, wastes a lot of material, wastes a lot of time. And I have noticed on the Ultimaker machines we have, adhesion is definitely a good idea. So I like to leave the adhesion on, and you'll see it's going to make like a brim around the part such that it sticks down better. So that's our settings. I can close that, and then I'm going to click slice, and it slices. And if you've got a small part, it should be pretty fast. Bigger parts will take longer to slice. And it's going to give us some info, and this is great. It's going to tell us it's taking 2 hours and 12 minutes to print this part. It's going to use 10 grams of material. Fantastic. This software, by the way, is free. You can download it from Ultimaker site. It should also be on the lab computers, and especially the computers in the maker space. So you can even like slice your stuff at home if you want, and then just bring your files in on a USB stick, and you stick the USB stick in the machine to print. You've got to leave the USB stick in while you're printing, so just be mindful of that. So like for the whole 2 hours, that USB stick is going to be in the machine printing. So that's great. It tells me some stuff, but I'd like to see like a better visualization of what this is going to do. So if I go over to preview, you'll see it changes a little bit. And this is showing me actually, this is like exactly the paths that it's going to print in plastic there. And I can use the slider on the right to step down through each layer to check that it's doing what I want it to do. And now we're seeing this like crisscross pattern. That's the infill. That's the 20% infill of the, where it's like, you know, the part doesn't need to be solid there. It's got these thick walls, and then it's going to have some infill. And then there's the base, and then there's our first layer. And so you can see also this is the brim, right? If I go to prepare, that goes away. That's the brim that's going to help it stick to the bed. So that's the basics of using Cura to slice your model. You save the file, put on your USB stick, bring it into the lab, and print. You're good to go. I will show you a couple other things here. So let me go back to prepare, and I'm going to rotate this around again. So it's upside down. And you'll see I have to reslice. Anytime I change something about the model on the bed, I have to reslice. So I'm going to look at this now. And in my settings here, I'm going to put support on. I'm going to see what it does to try to print these parts that I had said I think would be difficult for it to print without support. And I should say, it will always try to slice your model, even if you tell it to print something impossible. Like, it'll slice it and it will try to print it, but it might not work. So there's opportunities for user error here that you have to be mindful of. Okay, so we can see it's going to take 40 minutes longer to print. It's going to use 3 more grams, I think, of material. Why? Well, if we look here and slice through, there's our infill. There's still part. Okay, now this stuff, this zigzaggy stuff here, that's the support. And so that's printing it, and now you can see there's a lot of support in that open area at the top. The support material is going to be the same PLA, but there's a gap between it and the actual part that we want. And even when it does this like topmost layer, if I step through this really slow, so you see support, there's a support layer, there's not a support layer, not a support layer, and then it prints this. So there's a very small gap between the support and this. So this is going to deform a little bit, actually, like a whatever I'm doing, 0.1, 0.2 millimeters. is there's possible deformation there where this meets the support structure. But that will allow me to break off and dispose of the support material. And I'll do that with either just my hands or pliers to get that stuff off. But again, if I can print this without support, I would much rather do that. But again, be careful, because like if I say don't print this with support but still print it upside down, it will slice it and it will give me a file, that some G code that I could print. But I'm telling you, this would result in some errors when you're printing up and then suddenly it's magically going to put this layer just like floating in space like that. It's not going to work out. That's going to fall, and it's going to the part will fail. So be mindful. Always try to orient your stuff in the most sensible way to slice it. And I would say if you can print without supports, you're always going to have a better quality part without supports. So when you're thinking about how you design your models and stuff, try to avoid supports. Sometimes you can't avoid supports, and then it's fine to use them. But if you can, I'd say avoid them. There we go. There's our part sliced, ready to be 3D printed. And again, I save file, put it on a USB stick, and bring it in, and I'm good to go.